We defined deterministic finite automata. Now we're looking at non-deterministic finite automata. Non-deterministic finite automaton consists of an alphabet, a finite set of states, a transition function, a single initial state, and a set of final states. And the alphabet, the set of states, the initial state, and the set of final states is exactly the same as they are for the deterministic finite automaton. Now, as we said, this is now non-deterministic finite automaton. And so the only difference is that we have a transition function that takes a state and a letter and gives us a set of states. So if we have tau of q and little a, then that would be a set of states p1 through pm, where m is greater or equal to 0. 0, of course, denoting that there is no state at all present. And so if we go back to the example we had last time, that's why I wrote it down, just to remind you this is exactly the same automaton that we had, non-deterministic finite automaton that we had last week on Wednesday. So if you look at this, yes, you have from the initial state 0. Under A, you go back to 0. Under B, however, you go to 1 and 2. I used Q1 and Q2, but it doesn't make any difference. This is less writing, less scribbling, so 1 and 2. So under B, we go from 0 to 1, and as well to 2. So this is where now M would be 2, because we have two states that can be reached from 0. And then if we go further to state 1, under A, there is no transition, so there is nothing that would. And so if you have, say, the state, the word B, A, then that is, of course, going to create a little bit of an interesting situation, because if we have B, so we start, of course, as always, in the initial state 0, and now we want to find out, is there a path that gets us from the initial to the final state. So a path, of course, corresponds to a word. And so the question is there a path for a word W from the initial state to a final state? And if yes, then W is accepted. No, W is rejected. So this is quite the same definition as for the deterministic finite automaton. The only difference, of course, in the deterministic finite automaton is there is exactly a unique path for any word. That's no longer true. So if we look at the word BA, well, from 0, we can go to 1. And then from 1, using A, we can't go anywhere. So this path does not lead to a state, and therefore there is no path, and that means that this path ends in failure. But that's of course not the only path. We can go from 0 to 2, and then we go under A to 2 again, and 2 is an accepting state, and therefore the word is in fact accepted. BA is accepted by this non-deterministic finite automaton because we have a path that goes from the initial state to a final state. So by that definition, there is a path that for a word, in this case BA, from the initial state, in this case 0.
Professor, you're muted.
We can go from 0 under B to 2, and from 2 under A to 2, which means the word is accepted because we found a path that goes from the initial state to a final state. So that then gets us to the question, how do we define, well, first, obviously, we want to define tau of Q0 and W for some word W, because this is really ultimately what we are interested in. And then we want to define what is the language of all words accepted by this non-deterministic finite automaton. So as I hinted last time, when we extend tau to words, well, we have to do a little bit more work. In the case of the deterministic finite automaton, where we had tau from Q cross A to Q, we could simply then extend to tau to Q cross A star, which still gave us a state. That's for the DFA. For the NFA, we have to extend tau to words, but that requires that we do tau from sets of states and words into sets of states. So given a set consisting of states and a word, we are going to produce another set of states. And so if you look at this situation, obviously we have paths here for BA, but actually what we're really more interested in are the sets of states that capture everything that can be reached. So if we get BA, well, let me space this a little bit, BA, so we start with the state 0, and then from 0 under B we can go to state 1, but we could also go to state 2. And now from state 1 or 2, these two states, under A, well, from 1 under A, we don't go anywhere, so this isn't the empty set. And from 2 under A, we go to 2, which means that if we're interested in all the states that can be reached from the initial state using the word BA, then this is exactly the state 2. And of course, in this case, 2 is an accepting state, and therefore there is a path from the initial state to an accepting state, which means the word BA is accepted. So we have to actually define this, and so we have a set P, which is a subset of Q, and we have a word W in A star. And so the basis is tau of p and epsilon. So this is, if we have a set of states, p is of course p1 through pm, m greater or equal to 0. So if I have any set of states, capital P, a subset of Q, and I apply the empty word to it, what do you think should I get as a result?
You would remain at P?
Exactly. You
if it's
get
finite.
exactly P for all P, subset of Q. Nothing happens if you apply the empty word. You just stay wherever you are. So if you have these m states and basically you apply epsilon to each of the m states, well, you're going to get exactly the same states back. And then we have to do tau of p and w. And so in this case, we're assuming length of w is at least 1, which means we have tau of p a v. So we're assuming that w is a concatenated with v, where a is a word, a letter, and v is a word. So effectively what we're doing is we're splitting off the initial letter, which of course we've done here when we look at the word BA. Well, we split off the B and we discover that we can go from 0 under B to 1 as well as 2, and then we apply to whatever we have here, the set consisting of the states 1 and 2. We apply the remainder of the word, which in this case was A, and so from 1 under A we don't get anything, and from 2 under A we get 2, which means we effectively end up with the state 2. And so that means in order to mimic this behavior of tracing the word through the various paths that we have, well, we first take our set P and apply that single letter to it. And then this is, of course, now a subset of Q. To that subset, then we can apply the remainder of that word, which is V, and that then is the definition that we have. This is again for all P, subset of Q. And so this is a rather important sleight of hand that we did here, because effectively, if you think about it, paths can grow in number arbitrarily. You can look at, if you look at this automaton, well, if you just look at a bunch of B's and ignore the A's, a bunch of B's, for every 3 or 4 B's, you have a loop. You have either 0, 1, 2, 3, 0 or 0, 2, 3, 0. In both cases, a bunch of B's is going to give you a loop that gets you back to 0, and in 0 you have again a split. So you can easily see that if you play this out, say if you have something like 100 B's, then you're going to get a large, very, very large number of paths because you may take 4 B's in order to get 0. You may take 3 B's, and then once you're back to 0, you have again this possibility of splitting. So if we take just say 0, and then we have B goes to 1, or it goes to 2. and then we have 1 to 2, and 2 to 3, and 3 to 0, or 2 to 3 and 3 to 0. I'm sorry, 3 to 0. And then you can continue. So here you would get again under B a 1 or a 2. And here you have a 1 or a 2. And each of these is going to give you a new path. So that means that you're going to get, essentially, in this particular case, an exponential number of paths. It is, of course, clear, if you think about it, that these paths will only get you to, each path gets you to one of those 4 states. So collectively, even though you may have 100,000 paths, collectively they can go to no more than those 4 states, which means that in many cases you may have many, many paths to the same state. But inasmuch as we're asking the questions that a path for a particular word from the initial state to a final state, the only thing that is relevant is there a final state? We're not really that interested, if we think about it, in the paths. In particular, we couldn't care less whether there's a single path or a million paths to the same state. As long as we know that that state can be reached, we can test whether that state is final, and if it is, then the word is accepted. It doesn't make any difference whether that there are many, many paths or whether there's a single one. And so that means that effectively we're looking not at the paths, even though this is, of course, how we're defining acceptance. Is there a path from the initial state to a final state? But ultimately, we're interested primarily in, can we get to a final state? Which is, of course, now somewhat divorced from the notion of path, because we may have many, many different paths, or you may have one. It doesn't make any difference. And so that then gets us to the definition of the set of all words accepted by the non-deterministic finite automaton. This is a set of all W in A star, such that, well, tau of Q sub 0 and W, this is now, what is that? This is a subset of Q. By this definition, so we start in the initial state, we determine exactly all the states that can be reached using up all the letters of the word W. And we want to know whether one of those is a final state. Now, in the definition of deterministic, where this was a single state, we could just test, is this an element of F? Now, this, of course, in the non-deterministic case, is a subset of Q, and therefore the question, does this contain a final state, looks a little bit more complicated. Basically, we have to intersect that with the set of final states and determine that it is non-empty. So that intersection contains something, which means that that something in the intersection is a final state that is contained in tau of Q sub 0 and W, and therefore that is the ultimate test, whether the word is in the language or not. And so now this gives us the definition of the language of words accepted by the non-deterministic finite automaton. in. So that then defines the language, just like we defined the language of a deterministic finite automaton. The definition is quite similar, except in the deterministic finite automaton, this happened to be a single state, and therefore we could just test whether that single state was an element of F or not. Now we have to test, does this set of states contain a final state? And that means we have to take the set of states and intersect it with the set of final states and stipulate that that intersection be non-empty. And if it is non-empty, if there is a final state in tau of q sub 0 and w, then w is accepted, otherwise it is not. So that then allows us to define what the language is, and you can easily see that this is compatible with the definition of the deterministic finite automaton. Basically, if you look at the extension, well, the extension, if P is capital P is always a singleton, if there's only a single state, and the transition function is such that each entry in these columns is a single state, then of course it follows that everything that occurs is a single state, and in that case this definition for the non-deterministic case is compatible with the definition of the deterministic case. And so effectively what we can say, and given that the definition of the language is also compatible, if this happens to be a single state, then of course the intersection with F is the same as saying element R. And so they're all compatible. And that means that every deterministic finite automaton can be viewed as a non-deterministic finite automaton. So as a result, we can immediately conclude that whatever can be done by a deterministic finite automaton can also be done by a non-deterministic finite automaton. Obviously,
Professor.
Yes?
Professor, on that note, so this whole, all up until now, we were just trying to figure out whether or not a non-deterministic automaton could be made into a deterministic automaton.
No, we haven't talked about that yet.
Okay, so
we're only saying that a deterministic finite automaton is a special case of a non-deterministic finite automaton. That's all we've said so far.
Is it because all up until now, I was assuming that we were able to prove, just based upon the non-deterministic formula you just showed, that you could get to a single, I would assume would be like a single tau, and that way you can.
Well, you're getting ahead of things. At this point, I'm simply saying that every DFA can be viewed as an NFA. The next question, which is obviously the one you have in mind, is can we do certain things with an NFA that cannot be done using a DFA? Or conversely, can we show that whatever we can do with a non-deterministic finite automaton can also be done with a deterministic finite automaton? That's really the question you raised, right?
It actually wasn't, but that does follow along that line. So I'll go ahead and stop.
All right. Yes?
So just to make sure, one of the main things that we're trying to figure out is, how to actually build an automaton. And here we can actually determine that it doesn't really matter if we're using like paths, how many of the same path if it gets you to the same spot, giving you the same,
Correct.
right?
Absolutely correct. As long as you find one path, that's good enough. If you have 100,000 or only one, makes no difference as far as the acceptance is concerned.
Okay, so in that case, I think I follow now.
Okay? So we've established that every DFA can be viewed as an NFA, so everything that can be done, every language that can be defined using a DFA can obviously also be defined by using an NFA. Now, what about the converse? Are there languages that can be accepted by an NFA, but not by a DFA? If the answer is yes, then obviously NFAs are more powerful than DFAs. If the answer is no, then NFAs are equally powerful as DFAs. So let's look at an example, and let's look at the example that we had before. Let me write it down again. 0, 1, 2, 3, A and B. So we have it where we needed 1, 2, 2, 3, 0, 0, 0, 1, 1. This is the automaton. And now let's play a game. We'll start with the initial state, and we determine what we can reach from a state that we have encountered under a letter A and also the other letter B. So from 0 under A, we obviously get 0, and since that is something that we're looking at, we don't have to write it down again. So basically what this here is a queue of things that need to be considered. So from 0 under A, we go to 0, which is something we have already. From 0 under B, we go to 1 and 2, which is clearly something we don't have yet, so we have to write it down. So from 1 and 2, we have under A, well, 1 gives us nothing, and 2 gets us 2. So if we look at that, and of course, if you look at that definition, then probably we should explain a little better what we are doing here. So when we do this tau of that thing, we're basically looking at the union of all tau little p and a, little p in capital P. So this, we're taking the set capital P, we're splitting it up into all its components, states, and to each of these component states we apply the letter A, and then we form the union of those tau PAs. And that is, of course, a set, subset of Q, and to that we then apply V. So if we look at this in our example, well, we'll take, what do we get from 1 under A? Well, we get nothing. And what do we get from 2 under A? We get 2, so we take the union of the empty set and the set containing 2, and that'll give me the set consisting of 2. And then I'll do the same thing for B. Well, 1 under B gives me 2, 2 under B gives me 3, so I get 2, 3. And so I haven't considered 2 yet. It's not in this list, and I haven't considered 2, 3 yet. So in both cases, I have to write it down. So 2 then gives me 2 under A. That's straightforward. And under B, it gives me 3. Well, 2 I have already, 3 I have not considered yet, so I have to write it down. Then I have 2, 3. Well, 2, 3 under A, 2 under A gives me 2, 3 under A gives me 3, so the union is 2, 3, which of course I have already. And under B I get 0, 3. I'm sorting it so that it becomes more manageable. So 2 under B is 3, 3 under B is 0, which is 3, 0, and I'll write it 0, 3. And so 0, 3 has to be considered. Then I have 3. 3 under A is 3, which I have already. 3 under B is 0, which I also have already. So that is that. And then 0, 3 under A is 0 and 3, so the union is 0, 3, which I have already. And 0, 3 under B, well, 0 under B is 1 and 2. 3 under B is 0, so I get 0, 1, 2. So 0, 3 I have, 0, 1, 2 I don't have yet, so I have to write it down. So 0, 1, 2, well, 0 goes to 0, 1 goes to nothing, 2 goes to 2, so that gives me 0, 2. And 0, 2 I have not considered yet, so I have to write it down. And 0, 1, 2 under B, 0 under B is 1, 2, 1 under 2 is 3, and 2 under B is 3. So that's 1, 2, 3. 0, I'm sorry. Yeah, 1, 2, 3. Okay, 1, 2, 3 I have not considered yet, so I have to write it down as well. 0, 2 under A is 0, 2, same argument. And 0, 2 under B is 1, 2, 3.
Excuse me, sir?
Yes?
Is that one before supposed to be 1, 2, 2, 3?
Yes, but we're taking sets.
Okay, so we don't add the extra 2?
Yeah, there is. That's of course exactly the argument that we made against paths. The fact that we have many different paths to the same state, once we look at the set of states that can be reached, then all we need to do is write it down once.
I'm sorry. I thought you got confused there. Can we look at it again on 0, 1, 2?
0, 1, 2. 0, 1, 2. 0 is 1, 2.
Uh-huh. And then
1 is 2.
And where's your 2?
2 is 3.
Okay,
so you're looking at 1, 2, union 2.
Oh yeah, I'm sorry.
Union 3.
So we just
which is
1, 2, 3.
1, 2, 3.
Please excuse me. Sorry.
No. That's important because that shows me where you have problems, and so I can justify anything I do, but you have to tell me that you don't quite follow. All right? So does that clarify?
Yes, thank you.
Okay. So, any other questions? So then we have 1, 2, 3 under A is nothing, and 2 and 3, so that's 2, 3. 2, 3 we have already. And then 1, 2, 3 under B is 0, 2, 3. And 0, 2, 3 I don't have yet. 0, 2, 3 has to be written down in this queue of things to be considered. And so I have 0, 2, 3, which is 0, 2, 3. And under B, I have 0, 2, 3, which is 0, 1, 2, 3, which I haven't considered yet, 0, 1, 2, 3. And so this seems to be going on forever and ever. What does it? Well, the issue here is, of course, that even though it looks that it can go on forever, it is impossible for it to go on forever, because what we're having here is sets that are subsets of the total set of states, of the set 0, 1, 2, 3. And so these are subsets, but that means, of course, given that in this case we have 4 states, the number of subsets of a set with 4 states is only 16. And that means that in the worst case, we can get 16 states, 16 entries, 16 lines in this diagram, but no more than that. Okay? And that is, of course, a direct consequence of the fact that these are all subsets of the set of states 0, 1, 2, 3. And so, in fact, if we now do the next 0, 1, 2, 3, then we get 0, 2, 3 under A. And we get 0, 1, 2, 3 under B. And it terminates here. So what that means is that we have now enumerated all the sets of states that one can obtain in doing all possible words, because effectively this process terminates, and this is not by accident. It has to terminate because all of these, each line corresponds to a subset of the set of states. In this case, of course, the set of states is 0, 1, 2, 3. And each of these is a subset. This happens to be the full set. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of the 16 possible subsets of the set of states 0, 1, 2, 3. And now we're going to do one more little sleight of hand. We declare that initial state, which is the initial state of the original non-deterministic finite automata, also the initial state of what we have here. And then we do this test. This test basically said we're looking at the words, and so basically what we have been doing here is we systematically did that tau of q sub 0 and w for all possible words w. We started with the initial state, so this was tau of q sub 0, and all of these things that we encounter correspond basically to different words. So we're doing tau of q sub 0 and w, and generate all those sets. And as I said, this necessarily has to terminate because there are only finitely many subsets of the set of states. So in general, if you have n states in the original non-deterministic finite automaton, you will not get any more than 2 to the n states in the corresponding deterministic finite automaton, and of course now I've already indicated what we're going to do. We're treating this now as a DFA. And the only thing that is missing is to determine what is a final state. Well, we know already what that is. We test, does it contain a final state of the non-deterministic finite automaton? If it does, we will call that new state accepting. So 0 is rejecting, and so it is rejecting in the DFA. 1 and 2, well, 1 is rejecting, but 2 is accepting, so there is a final state in 1, 2, so we call this accepting. 2 is accepting. 2, 3 is accepting. 3 is accepting. Accepting. 0, 3 is accepting. 0, 1, 2, 2 and 3 are accepting. 0, 2, 2 is accepting. 1, 2, 3, 2 and 3 are accepting. 0, 2, 3, 2, 3 are accepting. And 0, 1, 2, 3, 2 and 3 are accepting. So what this is now I have a DFA which is D sub n. And so this DFA has the property that W is in L of n if and only if W is in L of D sub n by construction. So the language that we have in the original NFA, L of n, is exactly L of D sub n. And that then proves, of course, beyond any doubt, that whatever we can do with a non-deterministic finite automaton can also be done using a deterministic finite automaton. So the question, are there languages that can be accepted by a non-deterministic finite automaton, but not by a deterministic finite automaton? The answer to that question is no. Everything that can be done using an NFA can also be done using a DFA. But of course, as this example indicates, there is a price to be paid for that. The corresponding derived deterministic finite automaton may have many more states than the original non-deterministic finite automaton. And in fact, as I said, if you have in general a non-deterministic finite automaton with n states, your corresponding deterministic finite automaton may have as many as 2 to the n states. So you may have a non-deterministic finite automaton with 10 states, which looks quite manageable, and the corresponding deterministic finite automaton may have as but the key observation is, given any non-deterministic finite automaton accepting a particular language, I can always construct a deterministic finite automaton that accepts exactly the same language. And moreover, I can say that if the non-deterministic finite automaton has n states, the corresponding deterministic finite automaton will never have more than 2 to the n states.
So for a DFA, each number representing a position is itself a state. But in the NFA, a state can be composed of multiple different positions.
Well, I don't use the word position. If you actually want to graphically make it obvious, you just put a box around each of these, and that makes it a single entity. So 1, 2 with the box is a state, and 0 with the box is a state, and 2 with the box around is a state, and 2, 3 with the box around is a single state. And so obviously the box is kind of redundant after you've done it, but it becomes very clear that each of these things now is a state.
Right.
And for each state, under each letter, there is exactly a single state that you can get.
So in order for one of these to be a final state, though, not all of the constituent numbers need to be a final state in the DFA. No, only a single one.
That's right? The definition that we used in order to determine what is an accepted word by the non-deterministic finite automaton. This basically says if there is at least a final state in this set, then the word is accepted, and of course that means if there is at least one final state in this set, then the new state in the deterministic finite automaton is also accepting.
Okay, thanks.
So if you look at 0, 3, well, 0 is rejecting, but 3 is accepting, and therefore 0, 3 contains a final state of the NFA, and that makes that set 0, 3 an accepting state in the DFA. And so on and so forth. Okay. So at this point, we've basically established the equivalence of DFA and NFA. So if you say DFA, set of all deterministic finite automata, and NFA, set of all non-deterministic finite automata, and L sub something is the set of all languages accepted by whatever we have here, then we can state two things. DFA, the set of all finite, deterministic finite automata, is a proper subset of the set of all non-deterministic finite automata. That, of course, says that a DFA, a deterministic finite automaton, can always be viewed as a non-deterministic finite automaton, but there are clearly non-deterministic finite automata that are not deterministic finite automata. This one would be one of them, for instance. However, if we look at L sub DFA, the languages accepted by DFAs and compared with the languages accepted by NFAs, they are equal. Because, well, obviously, every DFA can be viewed as an NFA, so that obviously shows this inclusion. But using the construction that I've just shown you an example of, it follows also that the other inclusion holds. Anything that I can do with an NFA, I can do with a DFA, and so you have both inclusions, which means you have the equality. So if you want to define D sub n, then this is simply the set of, you have the same alphabet, you have a set of states, which is basically tau of q sub 0 and w. So we have an NFA, which is a q tau q sub 0 and f. And so this DFA is basically, the alphabet of course is the same. The set of states is those sets that we encounter when we start at the initial state and apply systematically words. Q sub 0 is still the set, tau first. So we have a mu. I'm going to define that in a minute. Q sub 0 is the same. And then the set of final states in the deterministic finite automaton is the set of all tau of q sub 0 and w, such that tau of q sub 0 and w intersection f is non-empty. And the only thing that we have to do is mu. So if we have tau of, mu of tau of q sub 0 and w and a, then that is simply tau of q sub 0 w followed by a for all w in a star. So that completely defines the derived non-deterministic finite automaton, and it is simply a formal way of writing down what we have done in this process. So with that, you can do the first question in your exercise set 1. Any questions? So now we have to define, if you recall, we were looking at a number of different ways of defining languages. And we've done basically the black box, the two black boxes, the DFA, deterministic finite automaton, the NFA, non-deterministic finite automaton. Now we're going to do regular expressions. Over the alphabet A. And so, as usual, these things are done inductively. So we have the basis, we have A in A is a regular expression. Denoting the language consisting just of that letter A. Now, you will probably think that the definition is a kind of brain-dead, very trivial definition. It may look that way, but that's somewhat deceptive. If you do arithmetic expressions, then it also looks kind of brain dead. You have a number n is an arithmetic expression denoting the value n. and then the inductive step would be if you have alpha and beta arithmetic expressions with values v alpha and v beta, then alpha plus beta, alpha minus beta, alpha times beta, and alpha divided by beta are also arithmetic expressions denoting the values v alpha plus v beta, and so on and so forth. So this looks just as ridiculously simple, and yet you can define all arithmetic expressions that way. And so the same thing is going to happen when we're doing regular expressions. So any letter in the alphabet is a regular expression denoting the language that just consists of that letter. Epsilon is a regular expression. Denoting the language consisting just of that empty word. And finally, phi is a regular expression denoting the empty set or empty language. Okay, so that is the basis. And now we can do the inductive step. If alpha and beta are regular expressions, denoting the languages L of alpha and L of beta respectively, then alpha union beta, alpha concatenated with beta, and alpha star is a regular expression denoting the language, well, L of alpha union L of beta, L of alpha concatenated with L of beta, and L of alpha, the whole thing starred. So these are this is the definition of regular expressions. And that allows us to deal with reasonably complicated kinds of things.
Could you go over the definition again, Professor?
Say that again?
Could you go over the definition again from point B?
If you have two regular expressions, alpha and beta, denoting languages L of alpha and L of beta, then alpha union beta is a regular expression denoting the language L alpha union L beta. Alpha concatenated with beta, alpha dot beta, is a regular expression denoting the language consisting of the concatenation of L of alpha and L of beta. And alpha star is a regular expression denoting the language obtained by starring the language L alpha. So usually we like to eliminate parentheses. Obviously there is an implicit parenthesization, so you would essentially start by parenthesizing everything, but that's kind of boring. You'd like to get rid of parentheses. And so the strongest binding is star, the next is concatenation, and the weakest binding is union. So if I have 0 concatenated with B star union B, then that is essentially the same thing as saying I do A concatenated with B star, and then that union B. Obviously, this is more user-friendly than that other one with 4 parentheses sprinkled over the expression, but it is essentially the same. Okay, so that means we basically have to do the B star first, and then we do the A concatenated with B star, and only after we've done that do we do the union B. So this is just like in arithmetic expressions, exponentiation is the strongest, binds the strongest, then comes multiplication, and then comes addition. So if I look at a particular expression, say A, B, union B star concatenated with A, well, how do I know that this is a regular expression? Well, I can do that test recursively. And using the definition, it follows that, well, this whole thing is a regular expression, provided this is a regular expression. And that is because if I have 2 regular expressions, the concatenation of the 2 is again a regular expression. And so, jumping right to the A, well, by definition of the basis, this is a regular expression. Okay? It says here that if I have a letter in the alphabet, then that is a regular expression. Obviously, this is a letter in the alphabet. We're assuming the alphabet is A, B. And so this is a regular expression, so this is a regular expression, but we still have to work with that. Now this whole thing is a regular expression provided this is and that is. Because if I have a regular expression here, A, B, and another regular expression here, B star, then the union of those 2 is a regular expression. Now, AB is a regular, so far I don't know whether these 2 are, so I have to continue going further down. So A concatenated with B is a regular expression, provided A is a regular expression and B is a regular expression. And by the basis definition, A is a regular expression and B is a regular expression, and therefore this is a regular expression, but we still have to continue with B star. Well, B star is a regular expression, provided B is a regular expression. So B is a regular expression by definition of the basis. Therefore, B star is a regular expression. Now I know that AB is a regular expression and B star is a regular expression. Therefore, the union is a regular expression. So we've now finally verified that this whole thing is a regular expression. Now you may say this is kind of pain in the you-know-where to do that, but actually this is quite useful. What we can do is we can turn this process around and use it to guide us through the steps that we have to take in order to go from the language of a regular, denoted by a regular expression, to a non-deterministic finite automaton that is derived from that regular expression. And of course, the idea is that the language accepted by that non-deterministic finite automaton is supposed to be exactly the language denoted by that regular expression. So again, let me belabor the language here a little bit. A regular expression denotes a language. A finite automaton accepts a language. Okay, so L of n sub alpha is the language accepted by this non-deterministic finite automaton n sub alpha. And L of alpha is the language denoted by the regular expression. If you go back to the definition of the regular expression, then it isn't just a recipe to form regular expressions. It also tells you exactly what the language is that is denoted by that regular expression. So a letter in the alphabet is a regular expression denoting the language that consists just of that letter. Epsilon is a regular expression denoting the language consisting just of the empty string. And phi is a regular expression denoting the empty language. And then we do the same thing for union, concatenation, and star. So in all cases, we are not just giving a recipe how to construct another regular expression, but it also tells us exactly what is the language that is denoted by that regular expression. So alpha union beta denotes the language L of alpha union L of beta, and so on and so forth. So ultimately then, given a regular expression, we want to construct a corresponding non-deterministic finite automaton, and then of course one step further, a deterministic finite automaton. That is something that we know already how to do. Once you're given a non-deterministic finite automaton, you can clearly construct a deterministic finite automaton. Now this process, which looks kind of strange and slow and laborious, of verifying that this is in fact a regular expression, if we reverse it and basically start with, so we have A concatenated with B. Well, A and B are regular expressions, and then B star B is a regular expression, and then we have concatenated with A. This is a regular expression. This is the basis. And then once we have all the basis elements established, then we can construct more complex regular expressions. So we have the concatenation of this regular expression with that one, which is A, gives us a B. And then we have the regular expression B star, which gives us B star. And then we can take the union of those two. And then finally we can take the concatenation of this regular expression with that regular expression. And that gives us then the verifies that this is in fact a regular expression. Now, that process of starting with the basis elements and then constructing more complex regular expressions is going to be mimicked precisely in the construction of the non-deterministic finite automaton for a given regular expression. Okay, so basically what we're going to do is we're going to show for every regular expression alpha, there exists a non-deterministic finite automaton in sub alpha such that the language accepted by this non-deterministic finite automaton of in sub alpha is exactly the language denoted by that regular expression. So what that means is that whatever we can do with a regular expression, we can also do with a non-deterministic finite automaton. And since we've already established that non-deterministic finite automata can do no more than deterministic finite automata, for every non-deterministic finite automaton, I can construct an equivalent deterministic finite automaton. It follows that ultimately I can construct a deterministic finite automaton for any regular expression. And so how do we go about that? Well, we're going to mimic exactly the way in which this definition occurs. Okay? We're going to take the basis, and so what we need then is an automaton for each of the basis elements, a non-deterministic finite automaton. And what does that automaton in each case have to do? Well, the automaton for that regular expression A must accept exactly this language consisting of the letter A. The non-deterministic finite automaton for epsilon, the regular expression epsilon, must accept exactly the language consisting of the empty string. And finally, the non-deterministic finite automaton for phi, the regular expression phi, must exactly accept nothing. And once we have that, then we can look at the inductive step. If we have two non-deterministic finite automata, one for alpha and one for beta, such that the n sub alpha accepts exactly the language denoted by alpha, and the n sub beta accepts exactly the language denoted by beta, then we can construct union automata, concatenation automata, and star automata, such that the union automaton accepts the union of those two languages, L sub alpha, L of alpha and L of beta. The concatenation automaton accepts the concatenation of L alpha and L beta. And the star automaton accepts L alpha star. If we can do that, then basically we can mimic this process. We start with the basis elements and then apply the various constructions: concatenation construction, star construction, union construction, and another concatenation construction. And the result is going to be a non-deterministic finite automaton for the regular expression. So that is basically the recipe that we are going to follow. And that is a construction that you won't find in the textbook. That's why there is a handout posted that describes precisely this construction, but we will go through it in all detail on Wednesday. Are there any questions?
Professor?
Yes.
Your I think TA's website is down.
Is it down? I don't know. I would have to check.
Yeah, I can't access it.
It is, yeah. A number of students have been talking about it.
Okay, I'll talk to. This is not my TA. This is just a student of mine who volunteered to put it up. So I'll follow up on that. But at this point, you probably want to wait until I go through it and then download it, because if you just download it cold, it probably is not going to do you much good. It's actually, it looks complicated, but it can be quite easily explained. Just bear with me and listen to my explanations on Wednesday. Any other questions?
Can you go back to slide 3? There was something I wasn't sure.
This one?
Yeah, for the 0, 1, 1, 1, 1s on the side, what does it exactly mean?
It means that this state, and of course these are now, each of these things here, each of the subsets is now considered a state of the DFA. This is an accepting state. So if we have 1, then it is rejecting, but 2 is accepting. And since all we need is at least one final state in this set, this new state in the DFA is accepting. This, of course, is exactly, follows directly from the definition of n, L of n, where we say, well, this is a set, and of course, all the sets that we get are these, nothing else. And then we test whether that set contains at least one final state, meaning that the intersection of that set is non-empty, and that's of course exactly what determines whether there is a 0 or a 1. Is that clear?
Yes.
Good. Any other questions?
Professor, can you go to the slide 4 so I can take the picture? Thank you.
4?
Yes.
This one?
Yes.
Okay.
Thank you, sir.
Any other?
Could you go through all of the slides?
Sure, I can.
Yeah, so can we take a picture?
All right. Slide 1. Slide 2 coming up. Slide 3 coming up. Slide 4 coming up. Slide 5 coming up. And finally slide 6 coming up.
Would it be too much to ask to just have you post these?
No, I don't post things. This is a synchronous online, and I do not want to get into the situation where everybody expects me to post things. I want you to be physically present and attend class. Once I start posting, everybody disappears. Sorry.
I have a quick question on, I think,
Sure.
slide 2. The slide with the table.
Slide 3.
Okay, 3. I can't. So again, on the first one, the 0, since B has 2 in it, that won't accept it. Is that correct?
Say that again.
So on the first entrance, the 0.
Right. Under A, you go to 0. Under B, you go to 1, 2.
And
0, you've already seen.
right.
And therefore you don't have to write it down. 1, 2, at this point in the process you haven't seen, therefore you have to write it down.
Write it down. And so we're not looking at anything in A and B as an accepted state. Otherwise,
No. It is strictly this first column that corresponds to the last column.
Okay. When we were doing this, the red squares, I got confused. Okay, so it is just.
Well, the red squares are simply so that you. I don't ever do that again, but this is simply to show you that we're now talking about this thing. So maybe the 2, 3 is now a single atomic entity. It is a state of that DFA.
Yes. Thank you.
And so I just put these boxes around so it becomes visually more obvious that this is one thing. So 2 is very different from 2, 3. And 3 is very different from 2, 3. All of these are 3 different states.
Thank you. Sorry.
No. I invite questions. I want you to ask questions because that's the only way I can see whether you followed what I explained or not.
So by accepting state, it means it's a final state.
Yes,
Okay.
in the DFA.
Understood.
Okay, so this is your DFA. The whole thing is your DFA. Now, you have, of course, the NFA. That started, this is what the NFA is all about. And the NFA had states 2 and 3 as accepting. But the DFA now has practically everything except 0 accepting. Okay?
Okay.
Other questions?
Wait, why isn't the first one accepting?
Because 0 is rejecting in the NFA. So if you take, well, take the question. So that means your W is epsilon. So you have tau of Q sub 0 and epsilon, which is, of course, Q sub 0. And Q sub 0, that's your 0. And the final states are 2 and 3. So you take the set consisting of 0, intersection with the set consisting of 2 and 3. And what is that? It's empty, right? Because 0 is not a final state, and therefore this is empty. And that means it is 0.
Oh, okay, okay.
Okay? Any other questions?
I have a question. Where
Sure.
is on the 1A where we have the slash?
One.
Yeah. So right here on the NDF, yeah, right there. I'm sorry,
We
not
have
on
one-
the actual.
We have 1, 2. Is that what you're talking about?
I'm talking over here on the other one. So you're
Oh.
on this graph. Yeah, so yeah. So
Oh, this
right
is
here,
the NFA. So under 1, from 1 under A, you don't go anywhere.
how does that show in this other one? Where's that step in this other one?
Look, your NFA, let me draw it for you. So you have, well, actually, I have it up here. There is your NFA. This is the NFA. That's exactly the same. I've written it down again, but it is exactly the same. So from 0, under B, you can go to 1 or 2. And under A, you go to 0, which is this. And from 1 under A, you don't go anywhere. So there is no transition. So you die. If you're in 1 and you get an A, you die.
So that's a dead state.
It's not a dead state because you can take a B and you get to 2 where it's in fact accepted. But if you have, there is no transition from the state 1 under A, which means 1 under A is nothing.
Okay.
Okay, got it.
Okay?
Oh wait, now I have a question on slide 3.
Yep.
So I remember you said that the first one was it was 0 at the end. So how about on 3 though? Because on 3, when it's a B, it goes to 0 and that's not a final state.
Who cares? The question whether a state is final is determined on the basis of that first column. I could erase all of these. All of the transitions could be erased, and you can still do that last column. Because the transitions are completely irrelevant for the purpose of determining whether a set contains a final state or not. The transitions are transitions, but they have no bearing whatsoever on whether a particular set contains a final state, which means whether that set of that new state is accepting or rejecting.
Okay.
So if I erased all of the transitions here, which I don't want to do, but I could, then you could still determine is a particular set of states of the non-deterministic finite automaton accepting in the new deterministic finite automaton or not. So let me give an example. For example, if I give you the set 0, 1. Now, this set is weird because you cannot get it. The set cannot be obtained by starting in the initial state and applying words. But it could be looked at, and obviously there are no transitions to 0, 1, but you can obviously say it must be a rejecting state because neither 0 nor 1 are accepting in the non-deterministic finite automaton. So both of these states are rejecting in the non-deterministic finite automaton. Therefore, there is no final state in this set, and therefore this set would be considered a rejecting state in the deterministic finite automaton if one could reach it. Now, you can't reach it because we are only looking at those sets that one can obtain by applying words to the initial state. That's, of course, why we get this list of states, subsets of the old non-deterministic states. But if I just asked you is 0, 1 in a deterministic finite automaton accepting or not, then the answer is no, because it does not contain any final state. Does that clarify it now?
Yeah.
Okay. Any other questions? Yes, 1, 2 has 2, which is a final state in the non-deterministic finite automaton. Therefore, it is a final state in the deterministic one. All right, so on Wednesday, then we will look at the construction from a regular expression to a non-deterministic finite automaton. We'll see you then. Bye-bye.
Thank you.